So most of the problems in the last video came from the fact that my test was not well controlled. I had changed a whole bunch of different things at the same time. I had changed the electrode placement, I changed the electrodes themselves with the conductive jelly, and I had changed the part of the circuit that had the common mode adjustment knob. And also I ran that test on a different day than the previous test, so there might have been a different amount of current flowing through the wires in the walls. And any of those things could change the amount of 60 Hz that gets into the circuit, and once it's in there, how much of it actually gets out. And on top of that, all the 60 Hz noise was covered up by other noise sources like muscular noise and cable movement noise, so it's really impossible to know just how well my circuit rejected all the common mode noise. So in this video I'm going to focus only on the common mode rejection of just my ECG circuit right here. And I'm going to do that by connecting the ECG to a tone generator instead of to my body. So I have an oscillator that I've made up of a 555 timer, and I'm going to feed the output to both of the inputs of the ECG. So the only signal at the input of the ECG is just some common mode audio tone. And so then I can adjust the common mode rejection of the ECG circuit in order to minimize the amount of that audio tone that I have at the output. So first I need to make sure it works, and since my oscilloscope is broken, the best way for me to do that is to put a little buzzer at the output. Yep, that works. And next, the ECG is an amplifier, so it's supposed to take small signals in. The output of my oscillator is going to be something like 0 to 4 volts. So I have this little variable resistor as an attenuator, which should reduce the voltage going to the input of the ECG. So I have a multimeter here set to DC volts at the output of the attenuator. So that should show the average voltage that's showing up at the input of the ECG. And I want to start with my attenuator set to give me no signal at the input of the ECG. And then during the test I can crank it up however much I need it. Right, so let's turn this on again. Right, you can see the average voltage there at the output. And then turn this knob until I get to 0. So that means there's no signal going into the input of the ECG. That noise is going to get old real fast. Now let's get this going. I've got the multimeter here showing the output of the DC offset tracker, just in case that sort of thing ends up being important. So let's start recording and then turn it on. So I have the attenuator set so that there should be no signal getting into the circuit at all. But I'm still getting a bunch of noise coming out of the output here. Let's see what happens when I adjust that attenuator. So right now the signal going into the circuit is getting larger. I don't like how that's changing the frequency of the oscillator. Let's see what happens when I adjust the, right now it's back down to 0 again. Let's see what happens when I adjust the common mode knob. That's also adjusting the frequency of the oscillator. And then this happens. And this is only from adjusting the common mode knob on the ECG circuit, so I'm not touching the oscillator right now. So right now I shouldn't have any signal going into the input of the ECG, so let's start there. I'm going to yank this out, so there should be nothing going into my ECG circuit, and look at what that did. So here it's important to remember that your circuit usually has more inputs than you think it does. So my ECG has more inputs than just the wires run to my electrodes, or in this case my oscillator. Its power supply is also an input, and if the oscillator is causing any voltage ripples on the power supply, then those oscillations get into my ECG circuit through the power connectors instead of through my inputs. So I can get around that by adding a big old capacitor across the power and ground, somewhere in between the oscillator and the ECG. Let's go ahead and toss this in, I think. There we go. Alright, so there we go. I got that big old capacitor across power and ground. So in my earlier videos I had a capacitor across the inputs of the ECG to act as a short circuit for radio frequency signals. This capacitor here is now doing the same thing, but for audio frequency signals across the power and ground. So this means I should have a much more stable power supply to the ECG that's not being kicked around by my oscillator. Let's see how this one works out. Alright, now let's start recording. Here we go, much less noise. And just to prove that this capacitor is doing it, let's yank it out. There we go, a lot more noise. Now I can start doing work. I've yanked out that buzzer because it was the worst thing in the world. So I'm going to start by turning my common mode adjustment knob all the way in one direction. That should create a really large imbalance. So any common mode that goes into the circuit should definitely be coming out. Now I'm going to start turning up the signal going into the circuit with that attenuator. And there we go, now I got a whole bunch of noise. So now I can adjust the common mode knob, and I should see it going down. There we go. Now somewhere around the middle of this dial it should get to its lowest possible point. Then it should start coming back up again. There it goes. Now it's coming back up again. Now I'm turning the dial in the closer to the other end. So that's what I expect the common mode adjustment knob to do, which is nice. So I'm going to turn this and try to minimize that noise. Alright, now I'm going to turn this signal up a little bit more and try to get it a bit more accurate. And that looks like about the best I can do. And now that I have the balance adjusted as best I can get it on my ECG, any 60 Hertz noise I have coming out of the output should be coming from, or at least mostly be coming from, an imbalance in the electrodes. It's also worth noting that when I was changing the common mode adjustment knob, and that was adjusting the frequency of the oscillator, that was before I had this capacitor across the power and ground. So not only can ripples on the power supply from the output of the oscillator get into the ECG circuit, they can also get back into the oscillator circuit and wreak all sorts of havoc. So that's what was going on there. And that's it for this video. I've made progress, which is nice. And in the next video I'm going to look into the electrode cable movement noise source and see if I can figure out where that's actually coming from.